Okay, so first of all, thank you very much for inviting me to this event. Since time is scarce, I will go straight to the point. So first thing I would like to mention is that we all know that we have a lot of applications in the line of sight that will require very flexible, fast, and power-efficient hardware to cope with increasing demand of bandwidth and connectivity. And I listed there a little bit, a bunch of them. So because of saturation of Moore laws, it's quite evident now that electronics will have to team up with other technologies to meet these growing requirements. And of course, one of the options for a partner technology is photonics. So photonics, in fact, is ideal because it's very complementary to electronics. It provides bandwidth, it provides low power consumption, and also it provides a vehicle for conveying information that is based on photons rather than on electrons. So there's been quite an activity in trying to produce first elementary systems that could do some very basic tasks in integrated photonics. And for the last, would say, 15 to 20 years, so there's been a lot of activity in what we call application-specific photonic integrated circuits, which are circuits that are targeted for a given application. The problem with the ASPICs, as I would call them from now on, is that they are difficult to. It is very difficult to have a good ASPIC in one shot. So you have to undergo through many processes, each of which can stop the overall flow because you need to either refabricate, redesign, or even assembly or encapsulation is not successful. So this is actually putting a little bit of overhead in the production times and in the cost of producing an ASIC. So one way to solve this problem is, which we bring from electronics, is a very simple idea, is trying to do something which is programmable. So actually the resources will be provided by a common hardware, and the idea is to be able to, if we are smart enough to design this product, to exploit it in such a way that it can be applied to multiple functions by suitable programming. And with that, we obtain two things. First of all, cost reduction, because we leverage on economies of scale, because it is always basically the same hardware that is produced. And on the other hand, with the second advantage is we bring a lot of added value through software. So just why reconfigurability? Because it brings adaptability and can allow you, for example, to correct fabrication errors. You have, for example, you design a given filter for an application, you can design a ring cavity, you go through your testing, your fabrication, testing, packaging, and then you go to the testing, and you see that your specs are not met. And that's because you have a fixed design. So you try it again, and you don't reach your target specifications. If you add reconfigurability, then you have internal settings that can allow you to really fix your specs internally once the circuit is fabricated and meet your specs, both in several requirements at the same time. So this is the added value of reconfigurability. So that will make you advance in your fabrication process. Second thing is that for doing that, you need a very basic and powerful tuning element, and this is what we call the Tunable Basic Unit. This is the heart. It is at the heart of reconfigurability, and there's many ways to do it, but a especially simple way is to use a 3 dB Mach-Zehnder interferometer, where you have a tunable coupler that is implemented embedding a balanced Mach-Zehnder cavity inside a 2-3 decouplers, and then you activate your a couple of phase shifters through voltage signals or current signals. So by doing this with these two independent controlling signals, you are able to activate or operate this unit in such a way that you can independently either choose whether your transfer power is going to be like a crossbar switch or an intermediate coupler, but moreover, you can independently switch or decide which is going to be your the phase shift that is going to be impressed in the transfer signal. So, key point: you control amplitude and phase, and with that you can build very complex circuits where you basically what you are going to do is you are going to manage the interference for multiple sources. So this is your new logic in photonics. It's not 1 or 0, it's not digital, it's phase and amplitude, and it is multiple interference management that is going to allow you a plethora of new functionalities. So this has been these units have been inserted in many different circuits. So there's like an evolution path from very most rudimentary to more evolved. So we started with application-specific circuits, where you include these very basic elements, perhaps with active elements like SOAs, but you have fixed circuit topologies. Then this has evolved to multiple interferometers, where you have like an input-output, multiple input, multiple output configuration, and only a feed-forward propagation. This is very good to implement all sorts of linear matrix applications. If you are able to change the settings of your TVU, then you'll be able to do basically any linear transformation. But the step forward is to do what we call programmable waveguide meshes and to embed them into a higher, smarter element that we call field programmable gate array. So waveguide meshes are used by replicating unitary cells, and the basic idea that we came across to replicate the same basic cells that you use in solid-state physics. Basically, you can sum this into 3 broad families, which is hexagonal, triangular, and rectangular. With that, and replicating these cells, you can build the 2D configurations, which are not, they don't have a specific topology, so they are application agnostic. And then you actually activate your tunable basic units to emulate any kind or different kind of circuits. Things that you can do emulate from very simple finite impulse response to ring cavities, single, multiple combinations. You can emulate interferometers. You can do almost everything. Okay. Furthermore, if you embed this into a smarter system that includes external high-performance blocks and also incorporates an electronic tire and a software tire, you can produce something which is very similar to your to the field programmable gate arrays in electronics, which, by the way, already nowadays amount for more than half of the market size of electronics. So this is our value proposition in Ipronics. Actually, is to embed this waveguide mesh into a bigger system, which includes your coupling to the exterior, optical coupling, your electronics, your controlling electronics, your RF biasing, and RF driving. But also, as I said before, the added value comes in the software. So this includes also the possibility of doing smart reconfiguration, placing of your components, self-routing, self-healing algorithms, self-recovering, optimization, performance monitoring, etc. So it's quite, we aim for a quite complete product that can be embedded in multiple applications: wireless, and also emerging ones like quantum computing, neuromorphic, data centers, interconnections, etc. So that's all I had to say. I think it's 10 minutes sharp. So thank you very much for your attention.